Previously, using a 100-ton hydraulic press, we tried to press coal and graphite into a diamond state, but unfortunately, we failed. And in the comments, I'm often asked to try this experiment using a 500-ton hydraulic press. Let's first understand how possible this is. For creating a diamond, graphite is better suited because the carbon content in it approaches 100%. The transformation of graphite into a diamond occurs at a pressure of 50,000 atmospheres and a temperature of over 1,000 degrees. The smaller the piston, the less force is required to achieve the same pressure. For example, for a piston of this diameter, to achieve a pressure of 50,000 atmospheres, it is enough to apply a force of only 96 tons. And for pistons with a diameter of 1 centimeter, it is enough to apply a force of 40 tons. Well, again, the question of the strength of the piston material is acute. The piston material is steel 45 hardened to 40 units on the Rockwell scale. I wonder what load this whole structure will withstand. The maximum load at which the piston deformed was 40 tons. That is, the pressure inside this vessel was about 20,000 atmospheres, which is twice less than required. The piston was crushed and got stuck inside the cylinder. And the graphite was compressed into this black tablet. Now we will try to extract graphite from there and examine it in more detail, for the presence of diamonds, of course. We will continue the experiment. The piston of the second vessel is made of high-speed steel. This is perhaps one of the hardest steels, if not the hardest. Hardness over 60 units on the Rockwell scale. The piston diameter is slightly less than 10 millimeters. The maximum load at which the piston was destroyed was 30 tons. The calculated pressure inside the vessel was no more than 40,000 atmospheres. As you can notice from this experiment, the strength and hardness of the top steel is not enough to achieve the required pressure. And we still haven't taken into account that all this should be heated to 1,000 degrees minimum. What if the piston is made of the hardest metal alloy, tungsten carbide? Tungsten carbide can withstand the required load. But theoretically, the maximum pressure should still be created at some point in the graphite. And in this experiment, using a tungsten carbide piston, we'll then try to achieve the required temperature. We will connect the upper and lower part of our device through copper electrodes to a wielding transformer, on which the maximum current will be set, 170 amperes. When the press starts pressing on the piston, the pressure in the vessel will begin to increase. We will turn on the wielding transformer and hope that an electric arc will appear inside. During arc wielding, the temperature of the arc is over 2,000 degrees. So, if all goes well, we will have more than a twofold temperature reserve. When the press developed efforts of 60 tons, we turned on the wielding transformer, and after a second, our circuit breakers were tripped. The light went out, but the press continues to hold this load. Within a couple of seconds, the light appears, the wielding transformer turns on, and the press finally destroys the tungsten carbide piston. We achieved a pressure inside this vessel of about 70,000 atmospheres, against the required 50,000. And whether any heating occurred there, whether an electric arc passed through, who the hell knows? I don't know what the temperature was inside the vessel, but it was definitely high outside. This is evidenced by the blackened and in some places melted copper wires. I just couldn't figure out how to take a closer look at all this. Nothing is visible to the naked eye here, just black graphite, macro rings for the camera lens, which in essence turned the camera into some kind of microscope. Let's try to examine these three piles of graphite in more detail using magnification. This is what the graphite looks like after the first experiment, where the pressure was 20,000 atmospheres. I realized what a diamond obtained from graphite looks like. These barely noticeable yellow inclusions are nothing more than diamonds. Who would have thought that you can create diamonds yourself? Of course, the cost of this method of obtaining is questionable, since in this case we used a 500-ton hydraulic press. The cost of a new such press is about $100,000. And our diamonds here turned out, let's say, not the largest ones ever. The diamonds turned out to be so small that I can only see them through this microscope, so to speak. They're not noticeable with the naked eye in this black pile of graphite. And these are yellow industrial diamonds. Their cost is slightly less than of natural diamonds. By the way, about a year ago, we tested technical yellow diamonds for strength with a hydraulic press. I accidentally managed to hook one of the largest pieces with the needle right here. Now, let's try to measure its size with a micrometer. The size of this piece right here is 15/100ths of a millimeter, which is slightly thicker than a human hair and is comparable to the thickness of an ordinary sheet of paper. And the cost of such diamonds, let's say of this size, is not very high. Write in the comments where, in your opinion, such diamonds could be actually used.